Okay, welcome back to the hydrocarbon bearing tutorial series. This is part three in the series, and I think there's only going to be three parts for this bearing because today we're gonna set up our bearing for a lamp simulation. We're gonna run the simulation, and then we're gonna play back the trajectory in SAMSON. I'm not going to cover the installation of lamps or anything related to the science of molecular dynamics. There are many great resources for that kind of stuff that out there, and I will put a link to at least one, maybe a few more, in the description for this video if you want to follow those. Of course, I want to mention that you can do molecular dynamics and even motion planning natively in SAMSON. I'd like to cover that at some point, but not today. Because you still might want to use lamps outside of SAMSON, and lamps is very feature rich. One example is you might want to apply some forces to various groups of atoms, and which I don't think you can do in SAMSON as far as I know, at least not yet. I should also mention that LAMPS can export LAMPS data files directly, and it can do so with a full topology. So it's going to include the bonds, angles, dihedrals, all that stuff. But for this tutorial, we're going to use AIREBO, and with AIREBO, you don't need the full topology. So instead, we're going to use a specialized script that I wrote that will give you a data file that's just kind of custom made for AIREBO. And lastly, before we get started, I'll mention that the general procedure that I'm going to cover in this video, it's basically the same I use for all the molecular machines I design. So you should be able to take the same concepts and the same steps and apply it to your own designs. And but I hope to still have many more tutorials in the future. This isn't going to cover everything. With all that said, now we can get into it. Okay, so once we have our model complete, which we have here for the bearing, then the first step is create jigs. A jig is a term that comes from a piece of software called Nano Engineer 1, or NE1 for short. NE1 was the first specialized molecular CAD package, so like a piece of software that was uh, specialized for doing this type of molecular machine design work. And I have a pretty long history with it, so I still use the term jig, and I still use the term extrude. That all comes from Nano Engineer 1. But you can think of a jig as a grouping of atoms that perform some specialized function in the simulation. So they might be atoms that you use for motors, or they might be anchor atoms, or they might be thermostats, stuff like that. In the context of lamps, a good way to think of jigs might be like a group of atoms that are going to get a specific fix applied to them. If you're not familiar with the term fix in lamps, just hang on, you will be. And in the context of SAMSON, jigs will be groups of atoms that just get assigned to a group. So that's what we're going to do. We're going to create two groups of atoms here in SAMSON that will ultimately be our jigs in our simulation. And so we need an anchor jig to keep the bearing stationary in space. And then we also need a motor jig to apply some motion to the bearing. So that's what we're going to do now. So we're going to just select some atoms. Okay, so the first group we'll create is the motor group, and we'll create that on the outer ring. Let's kind of line this up. If it helps, you can toggle the visibility. But really, all we want to do is create a couple of sort of symmetric bands of atoms. So I'm using the scroll wheel of the mouse to pan, and then the right button to rotate the view, and then you can always line yourself back up. So we're just try to maybe zooming in a little bit more will help as well. And we'll just select the band, and let's pan down, and then kind of line up the next band, kind of symmetric. And we're going to control to add to our selection. Push Control, select. Looks pretty good. Then there's a shortcut to add a group. It's just G. We could do it that way, or I believe it's also in the select menu. You can add a group this way. So let's select this band and we'll just call it motor. Okay. And toggle visibility. Now let's add the anchor group. Just do the same thing. Select some atoms. It doesn't have to be exactly this selection, but you definitely want to get carbon and hydrogen. Just select the band. It's alright for this. We don't have to be super precise for this one. Select those. Just anchor those. Looks good. Use the shortcut. And we'll call that anchor. Okay. Alright. We can see our selection. By right-clicking and select group nodes. I'm going to double check. But that should be good. Okay, so then we can move on to the next step. And for that, we're going to need to download some files. So if you go to my GitHub repos, if you go to the part library, which is called Diamond Machine Parts, and then within that library, there's the classic hydrocarbon bearing. So the files we'll need for a new simulation, we don't need all these. This is the total package, but we don't need it all. So bring to temperature input. We need the AIREBO force field. We need the energy minimization input. And we need the hydrocarbon bearing input. So this is what we'll do the molecular dynamics part of the simulation to apply rotation to the bearing. And then we also need this Python script, SAMSON to LAMMPS atom types. So at least get those. You can get everything if you like. But download those someplace convenient. And I already have. Excuse me. So if we look at SAMSON to LAMMPS script, just open that up. So what this is going to do is this is going to produce the LAMMPS data file that will hold the structure information for the bearing, but it's also going to assign atom types for our different groups. So we have free atoms that aren't assigned to either the anchor group or the motor group. We have two elements in that group. We have carbon and hydrogen, and then we also have carbon and hydrogen in the anchor group, and then we have carbon and hydrogen in the motor group. So we need 6 distinct atom types, and this is going to assign those numbers 1 through 6 for each of the appropriate atoms. Now, this is already set up. It's set up for my computer, and it's also set up for the hydrocarbon bearing, but you're going to have to make some changes for your computer. And if you also want to reuse this script for other systems, or other jigs or jig names, then you're going to have to make some changes for those too. I try to comment everything that needs to be changed. So we just go through this real fast. So your output directory, of course, change this. If I would leave this, the data file, this name, because the other input strips are going to be looking for this. But for any other system, go ahead and change that. And then we're in the jig groups down here. So a fair amount to change here. So we have our 2 SAMSON groups, anchor and motor. If you have given them a different name or you want different jigs, then you're going to have to edit this part here. And then these names are used a few more times down here through this code. But so free atoms, those are the ones that aren't assigned to motor or anchor. But anchor, and then there's motor down here. So like I said, it's not that bad to change and to edit, and I tried to call it all out everywhere you have to do it. But once you've got your script ready to go, we can go back into SAMSON. And then go to interface when we want to open up the Python console, like so. And we'll just run our script from here. Oh, okay. I'm glad this happened. I'm glad this. I I have so much respect for like people who do like those 2 hour Blender tutorials, and they have like the webcam pointed at their face the whole time. I wonder like how many times they have to get, how many takes they have to do. All right, so I noticed that this script has this issue uh, with placing the motor and the anchor groups in this position in the document tree. So, but if we take these and pull them up like this, outside of this initial hierarchy, and run the script again, it works. Okay, so the script will output some data. It tells you how many atoms there are. It tells you how many atom types are in the structure. Six, that makes sense. So there's carbon and hydrogen for the free atoms. It's what I call any atoms not assigned to a group. There are hydrogen and carbon in the anchor group, and hydrogen and carbon in the motor group. And then it will also tell you the centroid of the groups. So the centroid's like like the middle point of the group, and what you really need that for is if you're using a rotation fix in lamps, the rotation happens about the centroid. So we're gonna use that data in our input script. So we can just go ahead and select that, copy raw text, and we'll go to our input script, and we'll paste it in right here. So this is our fix that actually rotates the bearing. Again, like I highly encourage you to go through the lamps documentation so you know what these numbers mean in depth. But this is our fix name. This is the group that's being applied to. So it's being applied to our motor group. It's moving it. It's going to rotate. This would also can move in a linear direction, but we're using it to rotate. This is the centroid that it's going to rotate around. The point is going to rotate around. This is the XYZ vector that it's going to point to. So I think lamps uses the right hand rule. I'm pretty sure it does. So this is 0 0 x is 0, y is 0, z is 1. So it's going to point in the z axis as it when it rotates. And if you look, that makes sense. So this is our z axis. You kind of like so hold your right hand in front of you, point your thumb at your face, and then I think your fingers are going to bend in the direction the bearing should rotate. I think lamps uses that rule. I should know in depth, but I don't. And then this last number is the period of rotation. Okay, so I think this is the only thing we have to change for our script, and then we can go ahead and start running stuff. So let's bring up a terminal in our directory where we have all of our files, and then we'll just go lamps in. First thing we're going to do is we'll just do another energy minimization. It goes really fast. And next thing we're going to do is bring it up to temperature. So when this first starts, I don't want to get into too many details about molecular dynamics with this tutorial, but of course, there's none of the atoms have any velocities assigned to it. So we're just going to run a shortish little simulation that sort of steps brings the structure up from absolute 0 to 90K, and it's going to do it kind of in small increments. So we'll just go lamps in, bring to temp, and we'll let that run. Again. And we're back. So the bring to temperature script has just finished. It didn't get all the way to 90K. I think it got about 60K, which is fine for this So now we're just going to run our MD script, our third script. Hydrocarbon, capital B, bearing. And that's going to take a while. It's running pretty fast. But while that's going, let's just, one other thing I wanted to mention about it. Okay, so like I said earlier, this is the period for it. So this is 125 picoseconds, and then we have our time step as 0.00025 picoseconds per step. So to do one complete rotation would take 500,000 steps, which I'm not going to do on the computer I'm filming this tutorial on because it will take quite a while. It might actually just burn up the computer. So I have set this to 50,000, so we're only going to do about a tenth of it, or we should only expect the bearing to turn about 36 degrees. Okay, so with that said, I go back and I will cut to the end of the script when this finishes, and then we'll play the trajectory inside SAMSON. And we're back one last time. So that took just over 41 minutes to complete on my machine here. Now let's take a look at the results. Let's go ahead and just open a new document. That's fine. We'll browse and load the trajectory file. And it needs a structure file to go with it, and by default it will look for the data file with the in the same directory, but you could also use like a PDB or an XYZ, but it's gonna load the data file along with it. So we'll load it, and then we can select the trajectory, go to the inspector, then we'll play it, and rotates. So we could also add a visual style to it. Visualization, visual model, van der Waals. Play it again. There we go. So that's sort of the basic concepts of running the type of molecular machine simulations that I tend to post movies of, using SAMSON for modeling and preparing the atom groups for the simulation. So I hope you try it. These tutorials are a lot of work. So, but if they help anybody, then they're definitely worth doing. I'd like to do some more in the future. Let me know of anything that doesn't work out, any problems you have if you do try it, and anything I can do to make them make better movies. Thank you.